Hello everyone, this is your teacher Baymarks and today we will be discussing another topic on General Mathematics Module 16, which is representing real-life situations using exponential functions. For this module, we have the following objectives. First, define exponential functions. Second, show illustrations of exponential functions that represent real-life situations. Third, represent real-life situations using exponential functions. And fourth, solve problems involving real-life situations using exponential functions. I would like to start this module with a story entitled The Rice and the Chessboard Story, The Power of Exponential Growth. There was once a king in India who was a big chess enthusiast and had the habit of challenging wise visitors to a game of chess. One day, a traveling sage was challenged by the king. The sage, having played this game all his life, all the time with people all over the world, gladly accepted the king's challenge. To motivate his opponent, the king offered any reward that the sage could name. The sage modestly asked just for a few grains of rice in the following manner. The king was to put a single grain of rice on the first chess square and double it on every consequent one. If you were the king, would you accept the request of the sage? The king accepted the sage's request. Having lost the game and being a man of his word, the king ordered a bag of rice to be brought to the chessboard. Then he started placing rice grains according to the arrangement. 1 grain on the first square, 2 on the second, 4 on the third, 8 on the fourth, and so on. Following the pattern, how many grains of rice will there be on the 10 chessboard square? You can pause this video to answer this question. To answer the question, how many grains of rice will there be on the 10 chessboard square? Let us complete the table for the number of rice grains to be put on the first 10 chess squares. Here on the table, on the first square, we have a single grain of rice. On the second square, we have 2 grains of rice. On the third square, we have 4 grains of rice. And on the fourth square, we have 8 grains of rice. Looking at these numbers form a sequence. These numbers follow a pattern. And what do you think is the pattern? If 1 is the first term, 2 is the second term, 4 is the third term, and 8 is the fourth term, what pattern did you see? The pattern is, the next term is just twice the previous term. So from 1, twice of 1 is 2, twice of 2 is 4, twice of 4 is 8, and therefore, the next term is twice of 8 is 16. And 16 is the number of rice grains on the fifth square. On the sixth square, we have twice of 16 is 32. On the seventh square, twice of 32 is 64. On the eighth square, twice of 64 is 128. On the ninth square, twice of 128 is 256. And therefore, on the 10th square, twice of 256 is 512. And therefore, on the 10th square, there would be 512 rice grains. Following the pattern, we can immediately determine the number of rice grains on the 11th square. And that would be twice of 512 is 1024. But how about on the 20th square? How about on the 48th square? From the pattern on the table, We really need to know the number of rice grains on the previous square for us to determine the number of rice grains on the next square. And what did we do earlier? Yes, listing. Listing down the number of rice grains up until the desired square number. Can we do that up to the 64 chessboard square? Of course, yes. Though it's possible, it's impractical. For convenience and practicality, let us derive a formula out of the pattern that we have. Here on the first column, we have squared number from the first square up to the 64th square. And on the second column, we have the number of rice grains in each chessboard square. Together, let us discover the pattern. On the first square, we have a single grain of rice, and 1 can be expressed as 2 raised to 0. On the second square, we have 2 grains of rice, and 2 can be expressed as 2 raised to 1. On the third square, we have 4 grains of rice, and 4 can be expressed as 2 squared. On the fourth square, we have 8 grains of rice, and 8 can be expressed as 2 cubed. On the fifth square, we have 16 grains of rice, and 16 can be expressed as 2 raised to 4. And on the sixth square, we have 32 grains of rice, and 32 can be expressed as 2 raised to 5. From the table, what pattern did you see? Can you describe these numbers? These numbers are just powers of 2. From 2 raised to 0, 2 raised to 1, 2 squared, 2 cubed, 2 raised to 4, and 2 raised to 5. And now, let us observe the relation between the square number and the exponent of 2. On the first square, the exponent of 2 is 0. On the second square, the exponent of 2 is 1. On the third square, the exponent of 2 is 2. On the fourth square, the exponent of 2 is 3. On the fifth square, the exponent of 2 is 4. And on the sixth square, the exponent of 2 is 5. Can you now identify the relation? If we let x be the square number, and y, or f of x, is the number of rice grains, we can observe that the number of rice grains f of x is 2 raised to the square number x minus 1. And therefore, we have the formula f of x is equal to 2 raised to x minus 1 as the formula to determine the number of rice grains in each chessboard square. Now, let us use our formula to determine the number of rice grains on our first 10 chessboard square. And our formula is f of x is equal to 2 raised to x minus 1, where x is the square number and f of x is the number of rice grains. On the first square, the value of our x is equal to 1. Substituting 1 to our formula, we have f of 1 is equal to 2 raised to 1 minus 1. 1 minus 1 is equal to 0, and 2 raised to 0 is equal to 1. Therefore, on the first square, we have a single grain of rice. On the second square, the value of our x is equal to 2. Substituting 2 to our formula, we have f of 2 is equal to 2 raised to 2 minus 1. 2 minus 1 is equal to 1, and 2 raised to 1 is equal to 2. Therefore, on the second square, we have 2 grains of rice. On the third square, the value of our x is equal to 3. Substituting 3 to our formula, we have f of 3 is equal to 2 raised to 3 minus 1. 3 minus 1 is equal to 2, and 2 squared is equal to 4. Therefore, on the third square, we have 4 grains of rice. We can use our formula in determining the number of rice grains on our chessboard square. And on the 10th square, we have 512 grains of rice. Therefore, our formula f of x is equal to 2 raised to x minus 1 can be used to determine the number of rice grains up to the 64th chessboard square. In fact, we can use our formula in determining the number of rice grains granting the square number approaches infinity. The increase of the number of rice grains on the chessboard is an example of exponential growth. And we will be discussing this in detail in the next video, still part of Module 16. Following the exponential growth of the rice payment, the king quickly realized that he was unable to fulfill his promise because on the 20th square, the king would have had to put more than 1 million rice grains. On the 40th square, the king would have had to put over 1 trillion grains of rice. Now, let us use our formula to determine the number of rice grains on the 20th and 40th square. On the 20th square, the value of our x is equal to 20. Substituting 20 to our formula, we have f of 20 is equal to 2 raised to 20 minus 1. 20 minus 1 is equal to 19, and 2 raised to 19 is equal to 524,288 grains of rice. On the 40th square, the value of our x is equal to 40. Substituting 40 to our formula, we have f of 40 is equal to 2 raised to 40 minus 1. 40 minus 1 is equal to 39, and 2 raised to 39 is equal to 549,775,813,888. Adding the number of rice grains from the first up to the 20th square, we have more than 1 million rice grains. To be exact, we have 1,048,575 grains of rice. On the other hand, the sum of the number of rice grains from the first square up to the 40th square is over 1 trillion grains of rice. To be exact, we have 1,099,511,627,775 grains of rice. And finally, on the 64th square, the king would have had to put more than 18 quintillion grains of rice, which is equal to about 210 billion tons, and is allegedly sufficient to cover the whole territory of India with a meter-thick layer of rice. Now, let us determine the number of rice grains on the 64th square using our formula. On the 64th square, the value of our x is equal to 64. Substituting 64 to our formula, we have f of 64 is equal to 2 raised to 64 minus 1. 64 minus 1 is equal to 63, and 2 raised to 63 is equal to 9 quintillion, 223 quadrillion, 372 trillion, 36 billion, 854,775,808 grains of rice. Adding the number of rice grains from the first square up to the 64th square, we have more than 18 quintillion grains of rice. To be exact, we have 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, 709,551,615 grains of rice. It was at this point that the sage told the king that he doesn't have to pay the debt immediately, but can do so over time. And so, the sage became the wealthiest person in the world. Did you enjoy the story? What lesson did you get from the story? Now that we have our formula in determining the number of rice grains on each chessboard square, let us now have the formula in determining the sum of the number of rice grains from the first square up to the desired square number. If we let x be the number of squares, and g of x is the total number of rice grains, our formula would be g of x is equal to 2 raised to x minus 1. If we will be getting the sum of the number of rice grains from the first square up to the 64th square, our x is equal to 64. Substituting 64 to our formula, we have f of 64 is equal to 2 raised to 64 minus 1. And the sum of the number of rice grains from the first square up to the 64th square is over 18 quintillion. The formulas f of x is equal to 2 raised to x minus 1 and g of x is equal to 2 raised to x minus 1 are examples of exponential function. And we will be discussing exponential functions on the next video that we have. Thank you very much for watching, and I hope you've learned a lot from this video.